So good morning everyone. So I don't know if you hear me. Can you just tell me if you hear me? Okay, so it seems that you hear me now. So like last time we have a bit of lag between you and me, but I think it will be okay to interact with each other. So we are here together for the third and the last tutorial for Fluid Mechanics 2. So what we'll try to set up is probably that you try to work a bit on your own on the tutorial, and I will write some elements of corrections directly broadcasted here. So probably you should be able to see when I write stuff in the subject directly. So if you cannot follow for sure, you can just tell me, and I'm here to answer your questions. So this tutorial is dedicated to the applications of the momentum balance that we have seen together in the lecture of last week, no, beginning of this week. Okay, and we'll have two different exercises. The first one will deal with something which is the jet flow impacting on an obstacle here, and after, for the second exercise, we'll treat a slightly more complicated configuration of a wind tunnel, but let's see how fast we are going. But okay, so for this first exercise, we'll try to look at what is forces exerted by a water jet which is impacting a plate here. So this configuration was actually one of the practical session you may have done without the current situations, but it will allow you to have an idea of a quite simple configuration on how to treat the problem. So here you see, I let you read the subject. So you have a plane disk of radius r. So this is a disk. Okay, so you have a axisymmetric revolution around the z vertical axis, and you have a water jet with a circular nozzle here, where the flow is getting out here and is impacting the solid surface here. And the idea is, in this situation here, okay, so this is a kind of classical impact situation of in fluid mechanics. We will try to evaluate what is the force exerted on the obstacle here, which is a black object, and to see how we can apply this momentum balance to this configuration. Okay, so I have a small mistake here. I don't know why it's not working. So what we'll do here is that okay, so the subject is provided in yeah, the different questions are here, and we'll try to follow step by step on to solve the problem here. So for sure, so if you have any questions, so probably I will ask your questions directly, the one that you can write me in the chat, and at the same time what I'm waiting for you is that you try to solve by yourself the problem in order to understand and face the difficulties. Yeah. So as I was saying, okay, you have a water jet impacting this object here. So the first question is to give the expression of the force that we will denote F exerted on the solid obstacle as a function of the relative pressure on the viscous stress tensor in the water. So this means that here what I'm awaiting is in fluid mechanics, it's usually possible to express so the force exerted on the solid obstacle with those two informations here. So here what I'm awaiting is for you to express what is the force exerted on the total obstacle, so due to the force induced by water and also by air. So here let's say that it's very general fluid mechanics. Just try to write, okay. Where we are looking for the force exerted on a solid surface as a function of the inner forces, which are the inner forces of the fluid here, which are described by pressure and viscosity. So if some of you have elements, you can share it in the chat with your colleagues. Okay, so it seems that some of you have problems to hear me. I don't know, I can put my microphone louder if you want. You will just tell me if it's not too noisy, or I don't know. So maybe it's better like this. I don't know. Just tell me if it's okay, if it's better or not. Okay, so it seems that it's better, so you can try to push in this equation and just to write what is the form of the force exerted on an object. So what we'll consider is maybe that the surface of the object is made of different surfaces here. On here, okay, we'll just say that we look for the force of water on air. So we say that the object is defined with the surfaces which are provided here. So this is S2, which is in contact with the air, SV in contact with the air also, and SI, which is in contact with water. So do some of you have ideas about how we define the force exerted on this surface? So this is general fluid mechanics, where you should be aware that the force exerted on an object is always decomposed in two parts. So the force exerted by the fluids here are always expressed like two parts, which are a part associated to pressure on one part which is associated to viscosity. So if we write those two parts, it's just the integral over all the surfaces. So we'll try to write it. So this is the integral over those different surfaces. So this is the force exerted on the object. Yep, sorry, maybe I will just write it correctly here. This is the integral over the surface. Okay, so this is the integral over the surface of the pressure. The normal. So this is the integral of the pressure part. So this is the integral over the pressure on all surfaces of the object. Plus the contribution of the viscosity here. So this is the integral over the same surface of the viscous stress tensor. So this is okay. Okay, so once we have written this, maybe we can try to simplify a bit this expression. Okay, so if we just try to simplify, we can just note that what do we know about the force exerted here? We know that the air is a fluid at rest. Okay. So in the air, we know some properties about pressures and viscosity. So the air is the surface, the vertical surface on the surface S2. So the pressure is atmospheric pressure. And we also have one property which is associated to the fact that the fluid is at rest. By definition, this is just meaning that the velocity is equal to 0. And then, what can we deduce from this? If the velocity is 0, we can say something about the viscous stress tensor. So as a reminder, the viscous stress tensor is expressed as a function of the gradient of velocity. So when you have no velocity, the viscous stress tensor is also 0. On those surfaces. Okay. Okay, so for now, nothing very complicated. So this just allows me. So this is valid only in the air, the properties. Yeah. So this means that we can just rewrite the force of water. So the force. So here it's. So this is the force exerted by water on air. Okay. So the force exerted by water on air, what we can say is that the part associated to the viscous stress tensor, what is remaining is only the part on the solid surface, SI. And after, since we know that on surfaces SV on S2 the pressure is atmospheric pressure, on that surface SI SV S2 is a closed surface, what we can do is that we can, if we want, remove something like the contribution of atmospheric pressure over all surfaces here. So this is allowed to do this, since maybe I can write it down. So SI, SU, SV, S2, SV is a closed contour, and then we know that the integral of a constant function along the normal over a closed contour is always equal to 0. Okay. So this allows us for this expression to write that actually the force of air on water takes a simple form. It's actually just integral over SI of P minus P atmospheric along the normal ds. Okay, so this is due to the fact that on SV on S2 we know that the pressure is atmospheric pressure, so this is cancelled by this term here. And finally we obtain this form of the force. Yeah. So this should be very clear, because this is usually the first step you need to follow, is to be able to express what is the force exerted on an object in any kind of condition. But it's always expressed something like this, where you have force, which is a contribution of pressure on viscosity, and here you have only the surface in contact with water, which is named SI, so in interaction with water, with pressure, which is relative pressure, and viscous stress tensor here. So this is the general form of our force. And after we'll try to see, applying the momentum balance, how we find this force. Because we do not know for now what is the pressure and viscous stress tensor on these surfaces. So we'll apply the integral balance applied to momentum to be able to evaluate this force. But we need to know how it is expressed in its general form. So once we have seen this, so it should be pretty straightforward here. You can go on to trying to solve the question 2 here, which is to apply the momentum conservation equation to a given chosen system and to express the flow rate as to express the force, previous force F, as a function of the flow rate, the kinetic coefficient beta 0, the section S0, and the volume of water omega. So here this is the direct application of the momentum balance. So this is where you need to remind water how to apply this momentum balance here. So what I will do is that I will just wait a few minutes so that you can try to solve by yourself this problem. What I advise you is to refer to your lecture notes and to try to see how you can solve this kind of problem. Yeah. So I let you think about it a few minutes, and maybe you can ask me all questions you want in the meantime, trying to answer this. Yeah. So what I can maybe just advise you is that you will just maybe write what are the hypotheses. Yeah, maybe you can choose a control volume. Okay, it's usually the first step. You will define the control volume, refer the hypothesis, and write the momentum balance in its general form. And once you have written the momentum balance in its general form, you will simplify each term in the equation regarding the knowledge of the flow properties you have. So these are basically the different steps you will need to follow here. So I let you think about it during a few minutes. And if you have some questions about what I'm writing in my document here, just ask me. After, it should be this first question should be pretty straightforward. Yeah, just in a general way, how to write the force exerted on a surface. Yeah, which is just the integral of pressure and viscosity, viscous forces. Yeah. Okay. So do some of you have ideas about what kind of control volume we'll use in this configuration? It should be pretty straightforward regarding the configuration we have. I don't know if everyone is asleep right now, or if you are working on your own. So as a general concept, what you will try to, or what you will always do in this course is always to simplify the writing of this momentum balance, and you will choose a fixed control volume here. So this is a control volume which is not evolving as function of time. Okay. So since it's a fixed control volume, and as a reminder, we are doing balance over a volume of water, where you will identify inlets, outlets here, and from this balance, from the balance of momentum expressed within this volume, we'll be able to express some interesting properties. So here, the simplest way is to identify inlet, which is the output of the nozzle here, where the flow is getting inside here, and the outlets will be just the annular discus here, because there is a axisymmetric revolution here, which will be our outlets, will be the S1 surface, which is an annulus at a given distance from here. And here you have your circular plate, circular disc, which will be in contact with the water here. So this means that the volume of water, the control volume, sorry, as one is saying, we will use the volume of water omega as the control volume, and this volume of water, we will usually define it with different surfaces. This is a set of surfaces, so we'll write it. You have the inlet surfaces, inlet surface with, what do we have after? We have the one in contact with the atmosphere, which is named SE, like an exterior surface probably. We'll add the surface, which is mostly the outward surface, which is S1. and we add finally, to close the control volume, here we add the one in contact with the object, the obstacle here. So this makes you the surface here, SE, which is the two sides here, S1 and SI. So it needs to be, if you want to define a volume, the volume is closed. Okay. I can write it closed. With surfaces, this. Okay. So once we have written so once we have written our define our control volume, we'll be able to do the momentum balance. So there is one question of your colleague which is asking why the gravity does not account here. For the first question, we did not apply the momentum balance at all. What we have done is just to express from a fluid mechanics point of view what is the force exerted by the fluid on the solid surface here, and this force, it's just surface forces here. So that's why there is no gravity appearing in this expression of the force here, because the force exerted by the fluid, you have no gravity taken into account to express the force exerted by water and air on the solid surface here. You have the own weight of the object that may appear here if you want to express all forces exerted on the obstacle, but here we are just doing fluid mechanics, so considering what is the effect of water on air. From a fluid mechanics point of view, the force exerted by fluids, you have only surface forces here, because the forces are exerted through the surface considered, and it's going through pressure and viscous forces here. So, going back to our momentum conservation, we'll do a few assumptions in order to be able to express the momentum balance. So the hypotheses are, the first one is that we use a fixed control volume. And after, I don't remember what is said here. It is said that the flow is incompressible and stationary flow. So those are basically the hypothesis we'll use. Fixed control volume. We'll consider isovolume flow. And permanent on the isovolume and permanent flow. So actually we only need those assumptions for now in order to be able to express the momentum balance we have seen in the lecture. So this momentum balance, we'll be able to write it. Okay. So this is one equation that you need to know regarding those assumptions. Here, how to write the momentum balance. So maybe just to, yeah. So this momentum balance, you have different terms inside them. So you have the first term, so left hand side of the equation. It's give you something like rho v. So you have a term corresponding to the momentum flux through the surfaces, written like this. Okay. So the first term is the momentum flux through all surfaces. How much momentum is going through the outward part of the volume considered, so what is getting in or out our fixed control volume. So this is the left hand part of the equation, okay, so which is equal to the integral, so which corresponds to actually all forces, external forces applied on our volume. So the external forces are basically the volume forces, that we can express like an integral over the volume of rho g over the volume. Yeah, this is the volume. So here V is the volume. Okay. And after, the other forces are surface forces, which are as a general form in fluid mechanics, some integral over the surface of our volume, of the pressure over the surface, plus the integral the integral of viscous forces on all the surfaces of our problem. So this is the momentum balance applied on a fixed control volume defined with the surface. No, there is a problem. Yeah, so nobody saw this, but the inlet is S0. Sorry, so the inlet, it's not inlet it's inlet S0. Otherwise, we have 2 times the same surfaces taken into account. So inlet is S0, the nozzle, the exterior surface S1, which is the outlet, and SI, the surface in interaction with the solid. Yeah. So to obtain such kind of equation, you only need to do the assumptions of fixed control volume. On the permanent flow. you can obtain this. You can obtain this equation. So this is the most important equation you need to know in the expression of momentum balance. But once you have written this equation, you still have the simplification of all terms to do. Because here you can probably see that you have some integrals of pressure, viscous stress tensor on the solid surface, but you have all other surfaces that also have an important part. So once you have written this momentum balance in its general form, what you will do is to simplify each of the terms in the equation regarding what you know about the flow property on each of the surfaces. Yeah, the term associated to gravity, it's just something associated to the volume of water. Okay, so usually you cannot say so much about this term, but on all other surfaces usually you have informations about either velocity, pressure, viscosity, or different elements. So what we'll do, we can take the different terms and trying to say something about physical quantity we have. So if we take the first term here, it induces informations about velocities in the different surfaces S0, SE, SI, S1. S0, SE, S1, SI. What we'll do is that we'll try to see if we have informations about velocity here, and especially what we can say is in the inlet and outlet surfaces. Usually you cannot say so much, but we'll see how to simplify it. On the surface SE, which is the exterior surface, you can probably know a flow property about what's happening on this surface. Why? Because SE is a surface which is at the interface between water and air. So SE is actually a free surface between water and air. So it is a free surface. And actually, by definition, here, the free surface, or actually especially in this configuration, the free surface, when you have a jet like this, the free surface can be considered, sorry, where am I? Okay, it is a free surface that is the streamline of the flow, because the flow is delimited by this, so the water jet is getting out, and this is really a streamline, this free surface, this surface SE. A point on this free surface is staying on the free surface, and it's a streamline of the flow. So if it's a streamline of the flow, maybe we can try to do something like this. So if we are on a streamline of the flow, what we can say is that the velocity, by definition, if it's a streamline, we have velocity scalar the normal is equal to 0. This is the definition of a streamline. And after we have other property on surface, which is the surface in contact it is in contact with the solid surface. Okay, SI, this is the surface in contact with the solid. So we should know a property about what's happening about the fluid on a solid surface. This is simply the fact that, okay, the velocity is equal to 0 on this surface. So the velocity due to viscosity So this means that this first element, the flux of momentum, what is remaining is only information about inlet surface S0 on outlet surface S1. Okay. So what can we say about what's happening on S0 on S1? So for the section S0, yeah, maybe we can use section on surface if we take S1. So on surface S1, what can we say about surface S1? You can simplify also on surface S1. Surface S1, the flow is getting out, like here. The plate is horizontal here, and we have axisymmetric problem here around the z-axis. So actually what we can say is that what's happening on the left side is actually exactly the same as what's happening on the right side. What's getting in one side is getting out on the other side. What is getting out in one side is also getting out in all the sides, and this is axisymmetric. So due to the axisymmetry of the problem, and actually associated to the fact that we have the velocity scalar, the normal will be the same for any point in the outlet surface, but the velocity here is actually perfectly axisymmetric. So actually this integral, so due to axisymmetry, the integral will be identically 0. Do you write it? Due to axisymmetry, the integral will be identically 0 on this surface. Okay, so I hope it is clear. Just what's getting on one side is compensated by the other side on all the axisymmetry of the outward surface S1. So what is remaining is only what's happening on S0. So if it is only what's happening on S0, so what we can write, so this is so this means that okay, so it's actually equal to just the same integral over S0 . Okay, so we have simplified quite a lot because it's only the momentum flux is only what's getting in the problem. And what we have seen in the lecture is that the term in inlet and outlet surfaces, we want to express them since it's isovolume flow, we want to express those terms, the momentum flux through inlet and outlet surface using the mean velocity of the flow. Yeah. So this is where the kinetic coefficient beta appear. This is to express this expression, which is, so in the inlet, what we can say is that on surface S0, the parallel flow, okay, on isovolume also. It's parallel flow on isovolume, so this means that this rho v scalar n is something associated to the velocity square. And in order to simplify the writing, we use the kinetic coefficient in order to write this like as a function of u d0, okay, so which is the mean velocity in the inlet section. So this is rho beta. So this is the use of the kinetic coefficient multiplied by the section S0, which is directed. So the velocity is in this way, the normal is in this way. So velocity scalar normal, it's a negative sign, and after velocity and normal are opposite. So it will be directed along the normal n 0. So this is to simplify the writing of the equation. We introduce this. Okay. This kinetic coefficient that allows us to simplify the writing of this integral. So as a reminder, it's because we have parallel flow in inlet that the flow is isovolume that allows us to write. So since it's parallel flow v scalar n, yeah, maybe I can write it. So since it's parallel flow, the fact that it's parallel flow tells you that v scalar n is minus v and the velocity is also minus v, so directed along the normal n0 if we want to decompose it. Okay. So since it's parallel flow, you can express velocity in the inlet like v0 along n0 with a minus, and v scalar n is minus v0. So this gives you something like rho v0 square. The local velocity along the inlet surface here, n0, and you simplify this with v0, which is the local velocity inside the surface S0, yeah, which is changing inside the surface, and we relate it to ud0, which is associated to the flow rate. Yeah, probably we ask. Yeah. Yeah, but we can. I don't know, where did it disappear? I don't know. So this is something I can write it slightly more clearly. So we have all those terms, okay, and after we can, if we want, write it like, yeah, here it's a bit 0, so this is the kinetic coefficient inside the section S0, and if we want, we can write it as a function of QV. So this is Q V square okay. So we have this first term like this. So I hope it is clear to everyone. So the idea is just to simplify on each section, you know, what is the value of each coefficient, and after in inlet and outlet section you try to use kinetic coefficient to simplify the integral over velocity square using the mean velocity that I write ud, the flow rate velocity, which is associated to QV, like this. So this first term, this is what it gives. After what we can write this. This second term, this is okay, pretty simple. If this is simply this is just the weight of water. Okay, this is rho G omega, and this is pointing downward. So okay, the second term So momentum flex. After we have the gravity. After we have pressure forces and viscous forces. Okay. So the pressure forces, this is the term like this. So we'll do as we have done previously, namely we'll take each surface like this. You take each surface and you look at what do you know about pressure in all those surfaces. You see here you have 4 surfaces, you just look at do you know something about pressure on each of the surfaces. So if you know some information, you will simplify it, and if you do not know anything, you will not write anything. So surface SE, this is the exterior surface in contact at the interface between water and air. If we are at the interface between water and air, this is a free surface. So actually we know that this is a free surface, this is consequently at, what do you know, on a free surface the pressure is simply the atmospheric pressure. Yes. Okay. On the surface SI, which is in contact with the solid object, we do not know anything. Okay. Sorry, anything. Okay. On surface S1, on surface S0, actually we'll treat similarly those two surfaces. Surface S1 on S0. Yeah. We'll do a very classical approximation, okay, which is to say that on those surfaces, this is inlet and outlet surface, what we'll assume is that we have parallel flows in inlet and outlet surface. Okay. Surface S0, this is parallel flow. So when you have the flow in a cross section with parallel flow, so this means that the velocity is parallel to this, the velocity is parallel to the normal everywhere. We have one interesting property which tells you that in this cross section, so S1 and S0 are cross section, we know that, what do we know about pressure? We know about pressure that in a section with parallel flow, so with the streamlines which are parallel, in the section which is perpendicular to those parallel streamlines, the piezometric pressure is constant. So if the piezometric pressure is constant, this means that on section S0, so piezometric pressure, if you remember, piezometric pressure is P plus rho Gz. Okay. So piezometric pressure is constant in those two sections. So what can we deduce from this if we take the section S0? Section S0, Z is the same everywhere. So on section S0, piezometric pressure constant tells you that since S0 is horizontal, pressure is constant in S0. So actually, if you have a parallel flow in this section S0, which is a classical assumption we can do, okay, since the section is horizontal, the pressure is the same everywhere. And we can say something else about this pressure in S0. Yeah. The pressure is constant everywhere, but after, this is a nozzle which is getting out in the atmosphere. So this means that close to the outlet here, we are actually at atmospheric pressure. So this means that the pressure is atmospheric in all the section S0. And is the atmospheric pressure. On the surface S1, it's parallel flow, piezometric pressure is also constant, but this time S1 is not horizontal, it's vertical here. So the pressure is not strictly constant in S1. You may have some small variation of S1. But what we'll say is that the section S1 here, so we'll assume that this is a thin jet that we have in the outward surface, so that the variation of pressure will be very small compared to the other variation of quantities we'll have everywhere in the fluid, especially to what's happening on the obstacle. So this is one approximation. So what we can say is that in S1, piezometric pressure is constant, and assuming that the water jet is very thin in section S1, we can approximate that the pressure is almost constant. And actually, similarly to what we have on surface S0, in surface S1 on one side it's in contact with atmosphere here. So actually we also have it is atmospheric pressure. It is atmospheric pressure continuity at the free surface. So this means that, so yeah, we have a small approximation about what's happening on S1, but this is really a small approximation about pressure, so it's really almost atmospheric pressure here. In S0 it's exactly atmospheric pressure, in SE it's atmospheric pressure. So actually the term we add here, okay, so our pressure contribution, it's actually the integral of pressure over the section in contact with the object minus all other surfaces, and on all other surfaces what we have seen is that it's atmospheric pressure. So what we can do similarly to what we have done at the very beginning of this tutorial is to S0, SE, S1, Si, it's a closed surface. So we can add to this this just do so S0 so S0 is a closed surface, and then the integral of a constant value over a closed surface is equal to 0. So this means that I can approximate this, I can just add this term which is 0 here, just to cancel out all this term, and to have, as a reminder, we'll have only what is remaining is only what's happening on the solid surface with a relative pressure So this means that the integral of pressure terms over all surfaces of our control volume is actually ended up in only the integral of pressure on the surface in interaction with the solid surface. So this means we have simplified quite a lot the writing of our equation. So we have done momentum flux, gravity, pressure forces, and the only remaining term is viscous forces. So we just write it. Viscous forces, which is the last term. So for viscous forces, we'll use the same arguments that we have seen in the lecture. So we can take again do this. So on surface SE, so we'll start on SI, I do not know anything on the solid surface, because this is actually what I'm looking for. So on surface S0, okay, so on surface S0, what do we have? So on surface S0, we have parallel flow. S1, this is parallel flow. And what we have seen in the lecture, when it's parallel flow plus circular section, so actually the contribution of viscous stresses is identical, equal to 0 here. Plus isovolume, sorry. Term equal to 0. So on surface S1, what I told you about this contribution of viscous forces, it's when you have a parallel flow, actually it's only associated to the gradient of velocity that you have in this section. So assuming that we are getting out in air, actually we'll have a very small gradient of velocity in surface S1. It's also the same that we have on surface SE. Okay, it's not a parallel flow in SE, but it's SE is a streamline. So here it's a streamline. Parallel flow plus isovolume. So in inlet and outlet section, it's almost always that we assume that this is a very small term, which will be neglected here. Here on a streamline, it's also a very small term. You see at the interface you have water flowing here, and you have air. So the air is getting at the same velocity than water here. So you may have a small viscous contribution at the interface, but it's usually very small, and at least in this condition, where you have effect of inlet, the free surface, the outlet, those terms will be very, very, very small compared to here. So this means that we'll neglect what's happening on surface SE, S1. On S0 it's identical, equal to 0, but really those two terms, since it's sections where you have parallel flow or it's a streamline, so you have very small gradients of velocity, so it's really not a big deal to neglect those terms when it's a streamline, when you have a free surface. When you have a free surface, it's basically some viscous forces between air and water, which are two fluids, which are far smaller than the viscous forces you have at the interface of a solid, where the boundary condition imposes you to have a very strong gradient of velocity here. So this means that what we'll have is simply to assume that, well, this is really not a strong assumption, but this is something here. You can say that this is, okay, this is almost equal to what's happening on only the surface in contact with the in contact with the solid surface. So this means that we have finished our work here. So this means that summarizing what we have done, summarizing the momentum balance, we end up with, okay, so left hand side we have only one term, this term, which is equal to, sorry, to so the weight of the water minus this, okay, plus this two, okay. Oops. Plus, yeah, maybe here I can just write so the normal of along EZ, and here it's minus EZ, just to write it with the same, so it's okay. It's minus, okay, it's equal to this, okay. So this is what we have simplified. We started from a complex equation with a lot of contributions, and we simplified everything we could. And in the end, what we obtain is that by having just information about the inlet flow, the mass here, we're able to express what's happening on the surface of the solid surface. And if you look at this expression, what is this? This is actually simply minus the force of water on air. So this is why usually we try to express what is the force we are looking for in terms of integrals over surfaces. And when we simplify the writing of the momentum balance, we'll be able to make appear, here you see that this. So I just change N0 in minus EZ. So this means that the force of water on air is simply equal to it's equal to rho beta 0 here minus rho g omega. Here we are. So the force exerted by the fluids on the plate is expressed as this formula, very simple formula, where the force of water on air is simply function of only the flow rate square, here with the kinetic coefficient here, and something associated to the weight of the fluid. So that's the main objective of momentum balance, is to simplify the writing of forces by just knowing information about the inlet flow here, what's happening in the nozzle here, and of the geometry of the on the geometry of the control volume. Here you are able to obtain the force of water on air. Yeah, so that's a very powerful tool. Yeah. If you do the computations, you will find that this term is very small compared to this one, so most of the force exerted by fluid on the solid object is due to the momentum flux you have in the inlet, actually. And this is one basic property of flow impacts that you recover here. Okay, so after the last two equations, I will not treat them right now. So I can answer some questions if it's not clear to anyone. I will just cut off my microphone and just take a glass of water, just 5 minutes break. So during the, we can say that maybe we do a 10 minutes break. So I start again at 5 past 10, something like this. So if you have questions for this first part of exercise, I can answer them. Just ask them in the chat. And if you have no question, after you can start again on problem 2, where you will see that it's a kind of combinations of the last two tutorials in order for you to see a bit some practical applications on, for instance, how to extract, to evaluate the force exerted on an object, for instance, a car in a wind tunnel, how we can use such kind of our approximations, what we have seen to such kind of applications. So we'll see up to where we go in the solution of the problem, but we'll go for it just after the break. Okay, so yeah, for sure, if you have any question, if it was not clear, do not hesitate to ask. I'm free to answer questions which are asked in the chat, and afterwards at 5 past 10 we start again on the second exercise of the tutorial. So, welcome back everyone. So we'll start again this tutorial and we'll try to treat the second exercise. So hopefully you managed to follow the first one, so I did not get any questions, so hopefully it was clear to everyone. And we'll have a look to this second exercise. So for this second exercise, we'll treat you will treat the problem of wind tunnel. So the wind tunnel, the focus will be to treat this problem where you put, let's say, a model car inside the wind tunnel and you want to study what's happening in this wind tunnel, and especially you will investigate the fluid flow happening in this wind tunnel, and we'll study a bit at first how a wind tunnel is working. So this is this first case where we study just the wind tunnel in an empty configuration here, and for the second part we'll study with the car model and to study what's happening in terms of forces exerted on the car. So I think most of you have an idea about what is a wind tunnel, but some examples are shown in this figure 2, where it's used to study, I don't know, the force exerted, but also to study force exerted on objects, such as cars, but also to study more specifically some fluid mechanics problem, to do some flow visualization, for instance, like the one you see here. It's quite useful to have some experimental facilities such like this to study what's happening at model scale in order to possibly extrapolate it to full scale. Yeah. So here you can read what is written. Here we assume that the air moves in the wind tunnel. So the wind tunnel is depicted here, so you have something like a fan rotating on itself, inducing a flow which is in a closed loop, so the flow is accelerating up to reaching a steady state, and we'll study only the steady state. And here you have a testing area here, and inside this testing area we'll put objects like reduced car model or whatever. And inside this wind tunnel we have different elements. We have a first diffuser, which is changing the diameter from this one to this one. You have different corners with some specific devices to have a flow which is well organized. You have a convergent area here, testing area, second diffuser, and two other corners to make a closed circle. So we assume for sure that we have given viscosity, density, and here we treat the problem of a wind tunnel, so it is air. So classically we'll neglect gravity effects. So here, with respect to the presence of corner and so on, we have some head losses associated to the different elements with some characteristics which are provided to you. You have head losses in each corner. Between diffuser 1 and corner 1 here, in this location you have so you have different grids in order to homogenize the flow, to have a control level of turbulence inside the flow, and to have rectilinear, something like homogeneous flow, which have a given head loss coefficient which is quite large here, and we assume that the efficiency of the fan is known to a given value, yeah, that is provided, yeah, to a given value. So here there is something, yeah, it's a viscosity which is missing. We'll just add the okay, so you have different elements. Yeah, okay, so the efficiency is provided to you. Okay. So here we have two parts. For the first part, which is this part A, we'll study the empty configurations, which means we'll study this device here. And what is asked is to so we want the problem to work, yeah, we want the wind tunnel to work with a given flow rate of something like 100 meter cube per second. So here you need to keep in mind that, okay, so here's the section, where is it, ST? So the testing area here is something like 4 meters square. So this means the cross section is 2 meter by 2 meters. So this is a large testing area which is probably used to test cars at a full scale, or maybe small, yeah, small reduced scale, as we'll see afterwards. But this is a large equipment, a large facility here, because it's 4 meters square. And if you look at the flow rate, it's 100 meter cube per second. So this is a huge flow rate here. 100 meter cube per second. This is a huge flow rate here. So this is probably going very fast inside the testing area, as we'll see afterwards. So what we want to first know is what is basically the power of the fan you need to set up in this device in order to be able to satisfy the flow properties we want to achieve, especially the flow rate here. Yeah, and after we can do the calculation. Yeah. So what is said here is that the section area is pretty large here, and the distance in the circuit is not so long, so you will neglect regular and linear head losses here. Okay, so maybe we can start to have a look to this. So we need to evaluation of the power of the fan to be installed in the wind tunnel. So if we want to evaluate the power of the fan, in your mind, what kind of methodology will we use? Do you have any idea about the methodology we'll use to evaluate the power of the fan? If some of you have ideas, just write in the chat, for instance. Does it ring a bell of what do you use as methods to evaluate the power of a fan inside a fluid mechanics system? Just waiting for maybe some of you have some ideas. So I do not see any answers for now. So we want to evaluate an electrical power here. So a notion of power, this is something which is associated to energy. Okay, we are following an energetic point of view. So if we follow energetic point of view, it should always ring a bell that you will try to use generalized Bernoulli equation, because generalized Bernoulli equation, it's an integral balance of kinetic energy, which gives you ideas about energetic properties here. So when you have power to evaluate in a problem, in a hydraulic or aerodynamic problem, here always try to relate it to energy, so to most of the time generalize Bernoulli equation, in at least in the fluid mechanics 2 lectures we have together. So what we'll use is this generalized Bernoulli equation. So this will allow us to do a kind of recap of what we have seen in the previous tutorial of how we can treat the problem of the dimensioning of a pump, or here in this case of a fan, but the fan is acting more or less like a pump. So it's providing energy to the system. So if you remember, we have different steps in using generalized Bernoulli equation. The first step is to look at what is the fixed control volume at use. Once we have our fixed control volume definition, we'll check assumptions. And after, apply generalized Bernoulli equation by defining the different head losses on the turbo machines. On the machines at use. So if we keep this configuration, here what may be a bit tricky is to define what is the control volume. We'll use a fixed control volume that we can choose. Yeah. So I do not know if some of you have an idea about it. So we need to define one control volume. Okay, as a reminder, control volume need to satisfy some properties here, especially to apply it in generalized Bernoulli equation. So usually so for a generalized Bernoulli equation, so the control volume definition needs to be fixed. And usually we try to choose inlet and outlet with piezometric pressure constant. I'm waiting for some proposal about what kind of control volume I can use. In this particular configuration. So the control volume defines, you have one inlet, one outlet, and you try to relate what's happening in inlet and outlet with some property. And here we are interested in what we want to design is what is the power of the aerodynamic system, which is a fan here, which will induce the flow in the wind tunnel. Yeah. So what we can say is that we want to have information about the fan inside our problem. Yeah. So if you remember about generalized Bernoulli equation, maybe I can just remind what is this equation. We start to write while you are thinking about how to do it. So you have the head. So the head in the outlet minus the head in the inlet, which is equal to the sum of everything which is happening between outlet and inlet. So the sum of the linear and linear, sorry, yeah, you have this effect of all machines, okay. You have the effect of all machines which are changing the energy minus the effect of linear head losses minus the effect of singular head losses. Okay, so this is the general form. So what we need to evaluate to define our control volume is to have some dedicated sections where we have information about outlet and inlet. Yeah. So this should provide you information about what section you can choose as inlets and outlets. What I was saying is that we want to extract information about the fan. So one choice can be to choose one section before the fan and one section after the fan. It's legit to apply generalized Bernoulli equation between a section before the fan and the section after the fan. Okay, that's for sure that's possible, but in those sections before the fan and after the fan, since you know the flow rate, you know what is the mean flow velocity UD. So you know this term, you know it. in inlet and outlet. Okay, no problem. The vertical location Z, you also know it in inlet and outlet. Okay, but the problem is the pressure. I do not have any information in pressure in inlet and outlet here, so I will not be able to evaluate the left-hand side of the equation. Yeah. So here you need to think about a property of the flow problem that you study in this condition here, is that it is a closed loop. So the flow is getting here, and after getting out and getting again here. So it's turning on itself. So actually what it is possible in such kind of condition is to take the whole wind tunnel, this means the complete loop, as the control volume. So to start from one section, to take all the control volume and to end up with the same section. Okay, so let's write this. So one can choose to use the whole wind tunnel as control volume, so nothing prevents from it. Okay. So whole wind tunnel as control volume, and consequently to choose inlet and outlet sections to be the same sections. So what does this mean? If you choose the same inlet and outlet, this will just cancel out the left-hand part of the equation here. And it's actually explain you how the process of a closed loop is working in. The closed loop is actually a configuration where you have a machine, so left-hand side is equal to 0 here. And in terms of energy, the machine is providing energy which is dissipated in the head losses here. So you have an equilibrium between the energy which is bringing by the fan and the energy dissipated by the effect of viscosity in linear and singular head losses. So when you reach steady state, you have an equilibrium in a closed loop system between the input energy provided by the turbo machines, by the fan, and the energy dissipated by physical mechanism. So this is what will be the use of this. So as control volume, we'll use the whole wind tunnel. So the assumptions, so we'll assume that we study permanent flow on iso volume also. So assuming that, I don't know, yeah, it said that we have constant density, so this means that we can consider it iso volume. And yeah, we'll assume that yeah, that it's we reach steady state. Plus a fixed control volume, so it allows me to apply generalized bandwidth equation, and in this case with same inlet and outlet tells you that actually this equation reduces to, and since we have only so in terms of machines, what do we have? We have we have the fan, which is one machine. It is said in the subject that the linear head losses are neglected. Actually, we have the head of the fan, so the power provided to the system by the fan is equilibrated by the dissipation of energy due to all singular head losses. Yeah. So what remains to do is to evaluate all those singular head losses. So the singular head losses, you need to evaluate the different singularities. So the different singularities are provided in the subject. So you have corners, okay. You have the different corners. You have some grids between diffuser 1 and corner 1, and that should be it. Okay. So we have 4 corners on the grids. So this means that the sum of all those is equal to so you have to be careful about this definition of just looking for, I don't remember. If you remember, the general form of the singular head loss is the singular head loss coefficient multiplied by ud squared over 2g. So this is the general form of the singular head losses. You have the coefficient and you multiply by the flow rate velocity here. So in the configuration we study, what you have to be careful is that you have 2 corners which are on a large section S1 and 2 corners on a smaller section S2 here. So if you have 2 different sections, S2 and S1, this means that you have different velocities here, and you have to take into account the correct velocity. Okay, so you have 2 corners applied on the section 1, okay, plus 2 corners with section 2 that we can write if we want. We can write it with the flow rate ud1, so this is the flow rate velocity, this is the flow rate divided by the section. So this is 2 times this, so multiply, so ud squared is the flow rate. So this is so this is QV over S1 square divided by 2g plus the same is plus the same thing with the section S2. If you want, you can rewrite it like you can rewrite it like so multiply by 1 over S1 square, oops, plus 2 square, whatever. Okay, so it's just the different singularities you have in your system. So we are the four corners, oh sorry, and I forgot, you have the grid, and the grid is on so the grid, where is the grid? It's on the section S1, it's between diffuser 1 and corner 1, so it's on section S1. So please, plus the grid plus the grid over the same. So yeah, what we can maybe do, something like this. We want to shorten a bit the writing, plus the grid, so something like this. Okay. Oh, we know that S1 is 2, S2. Yeah, okay, so if we want, we can, yeah. We can even simplify. So since S1 is 2, S2, so it's 4s2 square yeah, after you can simplify as you want the different elements. If we just want to yep, I just need to multiply by 8 okay, yeah, after you can do it as you want. Yeah, I can even maybe write it like this. This is QV over, yeah, just rewriting a bit. It's maybe simpler like this. Okay. So okay, once we have simplified, after what remains to do is to evaluate the head of the fan. For the fan, so you should remind also that the head of the fan is associated to, is related to the power of the fan. So the power of the fan divided by rho G QV. So here this is so the hydraulic power of the fan, right? So the power of the fan from the hydraulic point of view, and what we are here looking for is the electrical power. So the electrical power is the electrical power of the fan to provide energy is larger than the hydraulic power. So here we should multiply by the yield. Is it whatever? So this means that in the end you are able to evaluate easily the power of the fan. So the power of the fan is equal to, so this rho GQV multiplied by this head divided by the yield. Okay, so this is the general form of the electrical power, and since you know that the head of the fan is equal to the singular head losses, you just need to multiply by this. You just need to multiply by this element in order to be able to find the value of the power of the fan. Okay, so after you can do the numerical calculation with the maximal flow rate. So you have everything. I think you have S1 is 12 meter square. You have the QV, eta F, XIC, etc. So you should have everything, and if you do the calculation you should find, I'm just checking, yeah, after you can do the computations at home. But I think you should obtain, I don't remember, several. Yeah, you can do the computations. If some of you do the calculation, you can provide the answer on the chat so that others can check. But I haven't done the. So here you will find, yeah, I don't remember, but it's several megawatts. It's because it's a very powerful wind tunnel that is studied here with a huge flow rate, which induce so okay, so so some of you can do the calculations. So one of your colleagues was asking, why did we ignore the linear losses? So we ignore the linear losses in this configuration. It's mostly because we don't have so much straight part with constant section. We have only this small section, this testing area. This, in terms of length, it's very small compared to all the changes of geometry we have. So what is more important in this particular configuration, those are singular head losses. This is why we are neglecting the other one, because we have a lot of singularities. We have the corners, the four corners, and the presence of the grid. Yeah. So you were also asking about the grid thing. So the grid is actually, I don't know how I can explain you. I can just try to see. I can just try to show something. I know the name. I'm just looking for. I'm just looking to show you. To show you what does it looks like. What does it looks like? Yeah, this is maybe, so this is devices which are put inside wind tunnels. It's just to have a flow which is very homogeneous. So you just put some, yeah, I don't know if we have some, I just wanted to show you images. Yeah, here we don't see so much, yeah, it's not here. But this is such kind of devices. This is such kind of devices which are put inside the wind tunnel here, on which very small holes, which makes the flow very more homogeneous inside your wind tunnel. Yeah, I was thinking maybe to find some examples, but it's not very clear. Yeah, I don't have really an example somewhere, but yeah, if you just Google a bit, you will find those different elements are present classically in wind tunnels. It's just to have a flow which is very homogeneous. Yeah, this is some devices like this. Yeah. Yeah, I don't have a very nice stuff, but it's usually something which is placed inside the wind tunnel at a given locations to make the flow homogeneous, so that in the testing area you are controlling very well the flow condition that you have. And since you are placing this inside the wind tunnel, it's inducing some specific head losses that you need to take into account here in this case, because as is said in the subject here, the grid here has actually a very strong head loss coefficient. Here it's 10. You see it's far more than the one induced by corners here, so that's inducing a lot of head loss. So that's important to take them into account. So I hope it's answering your question. Okay, so we know how to evaluate the power of the fan. Okay, so we know how to design our wind tunnel to obtain what we are looking for. So the part B will be dedicated to so I don't remember exactly. So after we want to evaluate, thanks to this wind tunnel, the drag force on the real car for the velocity, based on the measurement drag dm, which is at a model scale. Yeah. So we have two different lengths. We have the length of the real car and the length of the model car. So to evaluate the scale, what we need to do is to do a bit of a similitude in order to know what is the velocity, what is the scale of the model we'll be able to use. Yeah. So for this, we'll go quickly about it, but this is similitude. We'll use similarity, and what is said here is that in this kind of problem of the flow around the car here, it's well admitted that it's mainly driven by Reynolds number. You can do a pi theorem like we have seen in fluid mechanics 1 to deduce this. Yeah. So what we want is to have complete similarity between model scale and full scale. So complete similarity, as a reminder, this means that we will have a geometric scale. We have a scaling in length. So we have two different scales, and we want to keep the dimensionless numbers the same. Yeah. What is said here is that what is driven the flow is Reynolds number. Yeah. So what we'll do is just to keep Reynolds number the same. So it's pretty straightforward. This is what we have seen. So one of you find 0.9 megawatts. That's it for the first answer. Yeah. So maybe I can just put the value if some of you want to. If some others are doing the computations too, they can provide the answer. But, okay, if we go back to our Reynolds number, so what we want to ensure is that Reynolds number at model scale is the same than Reynolds number at full scale. What do I call V? The flow rate velocity in the testing area on the real. The real car. Okay, we'll say the Reynolds of the real car. So the Reynolds of so the Reynolds, by definition, this is simply so this is rho. The velocity of the model scale, that is the velocity in the testing area, okay. The length of the model scale divided by the density, the viscosity, sorry. So is equal to the same thing so is equal to the same thing for the real car of full length. Okay, so this should be quite straightforward. So in our condition we use the same fluid in model scale on the full scale. So it gives a relationship between the so it gives you that the ratio of of lengths between model scale and full scale, okay, is equal to the ratio of the real car over the test car. Yeah. So this is as simple as this. So here this is the ratio in length is equal to the inverse of the ratio in velocity. So once we have deduced this, we can know the scale of the model to, if we want to have the velocity of the real car. So to obtain the scale of the model, we need to look at, to fix the velocity of the real car. Velocity of the real car equal to what is named W, which is 90 km/h. Okay. And for the wind tunnel, the velocity in the testing area is equal to, by definition, this is the flow rate. We'll take the maximum value divided by the testing area. So you can do the computation at home in order to obtain the ratio of lengths so I let you think a few minutes about it. Just do the calculations at home and provide the answer in the chat. It should be easy to do. I'm just coming back. So I do not see answer yet, so it should not be too complicated. Maybe I have the answer somewhere. So the velocity in the testing area is something like 100 meters per second. If I'm not mistaken. 90 kilometers per hour. It's something like 25 meters per second. So this gives you something like, okay, there is one student aware, so it's a scale of 1/4. So this means that in order to test a car going at 90 kilometers per hour inside this facility, which is functioning at full rate, so with the volume flow rate of 100 meters cubed per second, you will test your car with a scale of 1/4. So this means that when you reduce the scale, you are increasing the velocity. So this is what is said here. When you reduce the scale, it's increasing the velocity. Meaning that here we are going at 100 meters per second in order to satisfy that the Reynolds number is the same with a smaller scale than at a full scale, or that the property of the flow are similar. Okay. So to finish, so to finish, we know now, okay, we'll test our car at scale 1/4, and we now want to study what's happening more specifically in the testing area. The testing area, which is here. We want to have a look when we put our car inside, what's happening. Okay. So what's happening? We have a car in the middle. Here we have inlet section, outlet section. And we are able to do measurements of the flow profile in inlet and outlet section. Inlet section pressure. Yeah, it's maybe not very wise. Maybe regarding the inlet section, if the pressure is P0. Yeah. P0, P1, beta. Yeah. So we'll maybe call the inlet section S0 and the outlet section S1. Just that it's clearer with respect to the definition of inlet pressure P0, outlet pressure P1. Here on velocity profile V0 and V1 in the outlet. Yeah. So we have devices to measure the flow in the inlet and flow in the outlet. For instance, you have pitot tube that you can move at different locations in order to measure the velocity profile you have in the outlet and velocity profile you have in the inlet. So the idea is to be able to express the drag force. So what is the drag force? This is the force exerted by air on the car, okay, as a function of P0, P1, the flow rate, the different sections, and beta 1, which is the kinetic coefficient beta. So here, if we are looking for, the drag force exerted on the car. So when you are looking in this configuration for a force exerted on an object, what you should think about is it should also ring a bell, and you should think about you should think about momentum balance. Especially that here it is said that we are looking for it as a function of information in inlet outlet on the surface and kinetic coefficient. Yeah. So if you followed what I told you, what we have done in the previous exercise, you should now know more or less what is the procedure you will try to follow. Yeah. So maybe I will detail a bit the procedure once again so that it's clearer for you. So we'll use this momentum balance and we'll apply it to probably the configuration we have here. So what I advise you is always, first part, you express the force that you are looking for as a function of pressure and viscous stress tensor. So in this configuration, the force you are looking for in its general form with the normal which is always exterior to the fluid, it's equal to, it's exactly what we have seen previously. This is the integral over the surface of the car of the pressure is the force exerted by the air on the car, so do not mismatch the signs. So here it's the force exerted on the car. So you have a part associated to pressure and one part associated to viscosity. So here it's just a reminder. Okay, so you have those two parts, part associated to pressure, part associated to viscosity. Okay, so it should be pretty straightforward. So what you will, after, in the momentum balance, you will look for those two elements to write those two elements as a form of the force you are looking for. So what we'll do, then we'll apply, we are looking to apply momentum balance. So in order to apply momentum balance, you need to define the fixed control volume of interest. Yeah. So here what we are looking for is what's happening on the car. We have information about inlet section, outlet section. It's pretty straightforward to use as control volume the whole volume of fluid, which is between inlet section and outlet section, delimited by the lateral sections which is a circular section like this on the surface of the car. Here. So this is the volume sketched in figure 4 here. So volume sketched in figure 4, made of the following surfaces. So the surface we have are, we have the inlet section that I called S0, the outlet section which is S1, we have what I will call the lateral section, which is the one outside of the testing area. And do not forget that the car is in the middle. You need to take into account the car because the car is not part of fluid, so you have to take these surfaces into account, the face of the car. Okay. So once we have done this, you have identified the control volume. What do? We check the assumptions of our problem. So I have a fixed control volume, stationary and ISO volume flow. So it allows me to write once again, just copy paste. It allows me to write this equation. I'll just change the surfaces of interest in our case. Allows to write the momentum balance under the form. So the integral over both surfaces this time. Okay, the part associated to gravity. This. And here we'll use the fact that it is said at the beginning that gravity forces neglected. So here, since we have a problem of, it is said, I don't remember where, it is said at the beginning that we can neglect gravity effect. Since it's small density, the effect of gravity are usually far less important than the other effect. It will just add the weight of air inside the testing area, so it's okay, so it's very small. Yeah. And after, once we have written the problem like this, we can simplify each of the terms as we have seen previously. Okay. So if we take the momentum, flux, the pressure forces and viscous forces. To change a bit, we can start with okay, viscous forces if you want. Just that I have seen that what is said in the subject is that the viscous stress at inlet outlet on solid wall can be neglected. So here it's provided explicitly that in the inlet outlet section on solid wall on the outside, we can neglect the viscous stresses. So this is once again very not a strong assumption in this configuration. It's because those viscous stresses are dominated by what's happening around the car. So what is remaining here is only what's happening in the car. Okay, so very easy. So if we take the momentum flux, what we'll say, we identify the different sections. So inlet section S0, outlet section S1, lateral section SL, and car surface of the car. Which is named SC. Yeah, it's lateral surface. So we have inlet section, outlet section, lateral section, lateral surface, and the surface of the car. So what we can do is we'll do very similarly to what we have seen. So in inlet section and outlet section, what is said in the subject is that the velocity profile in the inlet section, velocity profile, on outlet section, the flow is parallel. Flow is parallel and uniform. So if the flow is parallel, this is once again the velocity scalar, the normal gives you the velocity v0, and here the flow is even uniform, so the velocity is the same throughout the whole surface. So this term simplifies greatly. So this is equal what's happening on S0 so since the flow is uniform on this section, you can simplify the integral. So it gives you this integral for rho v0 directed along the normal n0. So the flow is parallel and uniform, so the integral is very simple to evaluate. In outlet section S1, the flow is still parallel, but this time the velocity profile is not constant. So what's happening in this case? We are once again using the kinetic coefficient beta, which relates the integral of the velocity square to the flow rate velocity square. Yeah. So this gives you plus rho beta 1 u d1 . So it gives you this term. So the beta 1 is to relate the integral of the velocity square. This gives velocity square since flow is parallel here, and to relate this integral of velocity square, this integral to ud square to the flow rate velocity. Okay, and after for the lateral surface, since it's a solid surface, velocity is 0, so this means the integral is 0. Surface of the car is the same, solid surface, velocity is 0. So actually this term reduces to the two components of velocity in the inlet and in the outlet. So this means that once again that I can maybe write so the normal on the outlet here is minus x, and here it's plus x, so we can just write it. We can just write it using the along x. So the inlet gives you a negative contribution and the outlet gives you a positive contribution. So then, once we have simplified this, the momentum flux, we can go to the pressure forces. This is the only terms remaining. So once again we can do the same. Okay, we'll use what is said here. It's said that in inlet section pressure is almost constant to P0. In the outlet it's the same. So this means that we can start to simplify this to so if the pressure is constant in the inlet section, it tells you that the integral over the surface is just minus 0 S0 N 0. Oops, sorry. So you have the same thing in the outlet with P1. Okay, so it's just because it said that the pressure is almost constant, which is a good approximation to have the pressure almost constant. Actually, what does it uses the fact that the flow is parallel flow in inlet and outlet section. So if it's not provided to you, sorry, if this is an information which is not provided to you, I can remind that it's coming from the fact that flow is parallel plus gravity neglected. So if the flow is parallel, what we have already used, it means that piezometric pressure is constant. And if you neglect gravity, this means that pressure is constant. Yeah. So it's actually what is used to obtain this. So for the pressure forces on the surface of the car, nothing can be said. You don't know anything about the pressure. Okay, so you need to keep this equation for the surface of the car. Okay, and after we can try to think about what to say about the pressure on the lateral surface here. So on the lateral surface, we can say something, yeah, just sorry. So what can we say about what's happening on the lateral surface due to pressure? So either we can maybe approximate that, okay, this is cylindrical stuff, so probably what's happening on one side may be compensated by what is on the other side. This is true if the car is far away from the boundaries. But in all cases, what we can say is that the pressure is in the vertical plane, okay, because the pressure is acting always normal. So the normal to the lateral surface will always be in the vertical plane. And by definition, the drag dm, okay, by definition this is actually equal to the force projected along the horizontal direction, along the direction of the flow. The definition of the drag, when you have a force on an object, usually we distinguish it in two parts. You have the drag on the lift. The lift is in perpendicular direction of the flow, and the drag in the direction of the flow. Here the flow is in x direction, so the drag is directed along x. So we can say, okay, we can say because after we'll probably do the projection along x. If we just do the projection along x, we'll do this. So which gives you something like n0 is along minus x. So we have minus minus, so this is plus. Okay, plus the term exerted on the term associated to the surface of the car. Yeah. So this means that if we recap what we obtain, so if we take this equation here that is projected, so if we take the projection in the horizontal plane of the momentum balance, if we recap, it gives us, we have this term, which is equal to, so the flux of momentum is equal to what's happening in terms of pressure plus we'll write it in a simpler form, so minus this plus the viscous contribution. Okay, so this is what we have obtained for now. And what we can see is that this term here, what is this term? It's actually, if I go back here, this is actually minus the force, and if it's projected along x, this is minus the drag we are looking for. The drag force exerted on the model car is consequently this is minus this term, so it's equal to this term minus this term. So this is actually not so complicated, and we are able to evaluate this drag easily So I don't remember what we have. Yeah, S0 and S1 are probably the same. Yeah, this is what is referred as ST. I can just rewrite it slightly. Because it's the same surface everywhere. So this is P0 minus P1 multiplied by the surface. This is okay, P0 minus P1 plus this is the part associated to pressure plus the part associated to momentum, which is ρ0 minus ρ beta 1 ut. Multiplied by everything multiplied by S T. Okay, and if you want, you can even change V0 on UD1 using QV because V0 on UD1, so here this is QV. QV over ST and since it's the same, so this is this square minus rho beta 1. So actually the mean velocity in the outlet is the same. It's still QV over ST. So this means we can even simplify. Is 1 minus beta, if I'm not mistaken. Okay. So after just rewriting of the equation, which should allows you to evaluate what is the drag force on the model which is applied. You should find a drag force I think you should find something like 400 newtons. And that's it. So here this is the second application where you see we have done exactly the same. At first you express the force as a function of pressure and viscous stress tensor that you are looking for, and after you define the fixed control volume, you check the assumptions, you write the momentum balance, and you simplify each of the terms on each of the sections. Yeah. Trying to simplify as much as possible, and in the end you should be able to write the force as function of informations in inlet and outlet sections. Yeah. this is what is really powerful in the momentum balance here. It is that in the end we are able to express what is the force exerted on this object by just measuring pressure and velocity in inlet section and outlet section. So we do not do any local measurements, just inlet section and outlet sections. And from those two informations we are able to recover what is the force exerted on the object. So I think after there is a last question, you can think about it at home. If you have any question, you can answer me by email. You can ask me by email for sure, but it should be straightforward, just how to go from model scale to full scale for the force. But the main objective here was for you to manipulate a bit the momentum balance, a bit of reminding about generalized Bernoulli's equation. So I think that's quite okay for me. So I do not know if you have any questions, so I will let you possibly ask a few questions in the chat. If you do not have any questions, I hope it was useful for you, this tutorial, and that it was pretty clear for you, and that you have all information in hand about for possibly working on the different elements we have seen in this course. As I sent you by email, there will be no practical work for fluid mechanics 2 due to the particular reasons. So let's see when the university will open again, if we have time to reschedule some of the practical sessions, but for now they are cancelled, and I'm just keeping the last practical session so that you will be able to ask me questions about the past exams which are available on the Hippocampus, so that you can work on them and ask me the question that you do not understand in the correction, for instance, so that it's clearer for you and you are well prepared for the exam. So thanks again everyone, so I hope everyone is okay, and take care in this complicated time, and I just stay online a few minutes if some of you got some questions. So thanks a lot, and otherwise bye bye everyone. So regarding the exam, it will probably be postponed when the university opens again. Since you are here up to May or June, it will be possible to do it as a regular exam when the university opens again. So it will not be online, probably. So it will be a normal exam, but I don't know when it will be. It's to be planned, because as you understand, the situation is not completely settled, so we'll see how we see. Okay. So no question about the tutorial. So I don't know if it's if for you it's a useful form of tutorial, just to see if yeah, for the preparation of the exam, if it was a good idea for you, so that you can follow about how to solve the problem, or if we should use another mean for you for this yeah, for this preparation of exam. I don't know. After it's open and to be discussed for any good ideas, they are welcome. But it seems that nobody got a lot of questions, so you were just yeah, probably listening. But yeah, one advice that I can provide you is really to try to solve on your own the problems, because it's how you are facing what are the difficulties, so that you are well prepared for the exam. So okay, so I will thank you once again, and see you another time. So we keep in touch by email about the possible postponing of everything, but you will be informed about it. So thanks a lot, and take care everyone, and see you another time.